Okay, so last time we had just barely started this discussion about arc length, returning back into Chapter 3, which we touched in very slightly previously. So we set up a bunch of notation and terminology related to little pieces of a parametrized curve. And again, this stuff is going to be really important in Chapters 6 and 7. We're also going to make some use here. But anyway, particularly important in Chapters 6 and 7. Okay, that said, how do we use this to solve a nice little easy starter problem? Suppose I want to compute the length, the overall length of a parametric curve. Well, the whole is the sum of the parts is kind of the point of view on this. So each little piece of curve, like that little piece right there, right? Well, we have a formula for what that ds is. ds is v dt. Right? So just plugging that in, and lo and behold, we have a formula for the whole as the sum of the parts. And in other words, a nice little compact little integral that we can use to compute arc length. So the example here is extremely plug and chug. It's just very straightforward, so I'm going to be super quick with this. But the question is to find the length of a certain parametrized curve and parameterization given. And notice all I'm going to do to compute that length is just copy this formula right there. Right? In particular, the magnitude of the velocity. Right? So you see we're taking the magnitude. Now I do have to take the derivative of the parametric curve to get my velocity here. Right? There's one little bit of calculus we have to do, but it's really just plugging in. And notice our bounds, the starting and ending points of the parametric curve become the bounds of the integral, and now it's just a matter of computing that integral. Side note, this particular integral is not a friendly integral, and we're not going to worry about how to actually compute this integral. Sadly, also, very often this happens, that when you want to compute the length of a parametric curve, you end up with an intractable integral. So very often, you'll notice this on my past exams, when I want to test this idea, I'll, instead of saying compute the length of the parametric curve, I'll say set up a single variable integral that would compute the length of the parametric curve. And there my intention is for you to get it down to this point right here. Okay. And then after that point, you just leave it. All right, everybody okay with this? Okay, so moving along. So let's talk about parametrizing curves. Now, you all remember, of course, that if you have an equation like this, in particular, if you're looking at a graph, then we have this handy trick called the graph parameterization that parameterizes it. Now, you can also notice, however, that this is also a parameterization of this exact same curve. And it looks weird. It looks, how could this be it's a quadratic. How could this is worse than a cubic. There's a sixth power in here. How could that be parameterizing our curve? But, just notice that if you plug this in for x, and if you plug this in for y, sure enough, y is, as it's supposed to be, x squared. So this satisfies the equation too, right? That's what an odd choice. Nevertheless, a perfectly reasonable, perfectly valid parameterization. Now, you can think of these as being independent of each other, but they're not in this case. And I don't want to get into the weeds of exactly when, under what circumstances you can do this. But the big idea I want to point out here is that there is kind of a substitution, you can think of it as, that turns the one parameterization into the other. In particular, notice, if I just take this first parameterization and everywhere I see a t, I put q cubed plus q, sure enough, the left parameterization turns into the right parameterization. So this is called a reparameterization. And there are moments when this is useful. So we're going to see one right now. The clever move that I want to do to reparameterize is if I have position as a function of time giving me a curve like so, I'm going to introduce a new parameter. The new parameter is just arc length. So specifically, let's talk about the details. We do have to designate one point as being kind of the starting point. And now remember, what I need to reparameterize is I need an algebraic relationship between my one parameter and my new parameter. Any sort of an algebraic relationship, well, there are conditions and details that I want to worry about. But if I can find an algebraic relationship between my new parameter and my old parameter, then it's just a matter of plugging it in. So here's the algebraic relationship. Given a t, my new parameter is the arc length. The amount of distance that my parametrized curve has covered in the first t, let's say seconds or whatever, units of time of that parameterization. Now, of course, we have a formula for how to compute arc length, no problem, given some time t. However far into your drive down this road we want to talk about, there's how you compute arc length. You'll notice I'm using a different dummy variable for the integral. I can't use t because here I've designated t as marking the end of the path I'm trying to compute the length of, so I can't use t for my dummy variable. It doesn't matter. Dummy variables don't matter. I'm using the Greek letter tau here just because it kind of looks like a t and it's vaguely suggestive, right? But it doesn't really matter what it is. So that's arc length, and once you've computed arc length, then, again, just like in the previous example, you just plug it in, and there's your reparameterization. And it's called the arc length parameterization. It's nice in the following ways. First nice feature I'll point out, it's intrinsic to the curve. Let me return to my metaphor of driving down a road. You can drive down a road in a lot of ways. Right? You can floor it drive super fast, right? And then slam on the brakes because you see a cop, and then you can floor it again and go super fast, whatever. That's one way to do it, right? Or you could just set the cruise control at 55 and take a nice leisurely trip down the road. Whatever. These are perfectly different ways, perfectly reasonable, nothing wrong with different ways of driving down the road. You will be at a different location after a given amount of time, depending on how fast you drive. So those different ways of driving down the road depend on the driver. Right? Depends on how fast you're driving. An arc length parameterization does not have that arbitrariness. Arc length parameterizations are intrinsic to the curve. After you've driven 17 miles, that's where you are. There's exactly one point on the road that is 17 miles beyond that starting point. It doesn't matter how fast you drove there. Right? So an arc length parameterization is natural. It's only dependent on the curve itself. It doesn't depend on how you drive on the road. So anyway, that's kind of a cool thing, this naturality. Here is another cool thing, kind of related to that, frankly, is this idea that it has unit speed. Notice all I've written down here is the single variable chain rule, vector valued function x, of course, but it's a function of s. S is a function of t, single variable chain rule. And then taking the magnitude of both sides, we look at this. That's the magnitude of the velocity, otherwise known as the speed. Now let's look at this thing over here. That's distance per unit time, otherwise known as speed. These two things are the same, and that means that this is 1. So the fact that this is 1, what this tells you is that your new parameterization, when you're looking at position as a function of s, distance, not time. Forget t, right? The crazy driver is driving however they're going to drive, right? That's no. Position as a function of distance traveled. Locations of the mile markers, right? The velocity of that parameterization is 1. So, unit speed. Neat fact. Here's the bad news. As we saw, computing arc length gives some nasty integrals. It also gives you some nasty resulting equations. And so as a result, most of the time in practice, analytically anyway, it's impractical to compute arc length parameterizations. They serve some nice sort of abstract purposes, but we're not going to use them hardly ever in practice. So just as a way of showing how hard this can be, look, here's a parametric curve, and let's see how this works out at the end. Now notice I start by computing arc length and yada, yada, yada algebra. We'll come back to that algebra in just a second, but even with a, I'm going to say, fairly nice result computing arc length, right? I got lucky that, look at how horrifying this integral was shaping up to be, right? I mean, it looked like it was going to be really nasty, but it all worked out, and I got an answer. And yet this is still something hard to work with, because I would have to solve for this t right here in order to be able to plug that formula for t in to reparameterize. And I can't solve for that t, it's in a cubic. Right, so, gosh, that's annoying. So, like I say, actually executing arc length parameterizations is often not realistic. So, anyway. Okay, all right, enough of that. Any questions about any of this? All right, moving along. So, new object of study. We're going to study something here called a vector field. This is a new thing. It is got a pretty simple definition, actually. A vector field on Rn is a function whose domain is Rn and whose target is the same Rn. Rn to Rn. Now, that's not how we tend to think about it. In practice, the way we tend to think about it is a picture like one of these, and these pictures come from visualizing such a function in a certain specific way. The input points from the domain are to be viewed as points, such as that point there or this point here. And then the outputs are to be understood, interpreted as vectors. And now how do we represent vectors? We represent them with arrows. And the convention that we're going to take here, standard convention, is that that output vector will be represented with an arrow whose tail is at the point in question. So that's how we make these pictures. And now notice if I have a function that gives me for every point in the domain a corresponding vector represented by a green arrow, then get one of these pictures kind of like this, right? Because you can do this for every point in that domain, and this is how we draw vector fields. So again, algebraically, formally, a vector field is a function, but in practice, a vector field is we think of it as a picture where at every point there's an associated arrow. How we doing? Everybody on board? Okay. All right. Okay, so let's see some examples. A couple of quickies, starting with this one right here. Let's see here. For every point x comma y, such as, for example, let's say that one, here's the field vector, 2 comma 1. Now, as per our rule, I'm going to represent that by an arrow with its tail at the point. Now, at other points, other x comma y's, right, different points, well, I'm going to have to plug back into my formula here to get, it's always, in this case, conveniently always exactly 2 comma 1, and so I get the exact same vector at every one of these points. So this is a graphical representation of what that particular, what we call a constant vector field looks like. Is that all right? Now I've got to emphasize one thing here. This is not a graph. Right? If it was a graph, it'd be 4-dimensional. 2 input variables, 2 output variables, 4-dimensional picture. We can't begin to draw that, and certainly this is not that. So it's not a graph. It's also not a level set. It's also not an image. Right? This is not like any of the pictures that we've ever drawn previously. This is now arguably a fourth different kind of picture. And there are different sort of relationships between the algebra of the function and the geometry of the picture. Notice, for example, this being a constant. A lot of people might have, thinking about graphs, a lot of people might have been expecting something vaguely horizontal in the picture. Nothing remotely horizontal in this picture. So anyway, don't conflate picture types, right? It's a really easy mistake to make. Graphs are not level sets are not graphs, which are not images, which are not vector fields. Okay. All right. Let's see the next example here. Do like that. Ooh, too far. Okay, so here we go. At this point, x comma y, some point like that, our field vector, now let's be careful about this, that field vector, also x comma y. Tempting to say that they're the same. Now, they're kind of the same. There is this little sticky wicket. The input is to be viewed as a point. The output is to be understood as a vector. Right? So they are different in that sense, but algebraically they're the same. And of course, points correspond to vectors. And if I want to understand this point as being a vector, that vector is the position vector. And so I can now say that this field vector is the same as that position vector for the point. And of course, now with my convention being that I draw it with the tail at the point in question, then this is how I actually draw that field vector. What do you think? Everybody follow that? Now, blanks for y'all to fill in for yourselves. If you repeat this process and draw the sort of the analogous picture for every point in the domain here, then what you will find is that you get a picture that looks kind of like this. So you can sort of see, we had previously been looking, at that point we had this field vector, and then likewise at this point we have that field vector, and you sort of keep going throughout the picture and you get this sort of radial outward sort of vector field like that. Everybody happy? Okay, next example. Just to, kind of get our feet wet and see what some of these things look like. Here we go. What about this one? It's not a constant. The output's not the same as the input. I guess you could plot some points and just kind of hope that the pattern presents itself. I will point out here there's a clever observation you can make. This won't always happen, but it's always good to be on the lookout for convenient, clever observations. Your point that you're looking at and your field vector that we're going to draw momentarily, you'll notice they both involve coordinates being sort of x's and y's, plus or minus. Based on that, it's pretty easy to notice, hey, check it out, they have the same magnitudes. And then you also notice, because of that minus sign, they are orthogonal. Right, so a couple of clever observations, and we've immediately reduced our options to these two. Not sure immediately for sure which one of these it is, but it does have to be a vector that has the same magnitude as the distance from the origin and that's perpendicular to that radius. So these are the only two options right off the bat. Everybody on board? Now how do we decide which one it is? A little bit of linear algebra is going to help us out here. I'm going to remind y'all that you should be really good at this point at the particular task of finding matrices that represent linear transformations, right? And specifically, rotations are linear transformations. So I want y'all to use your linear algebra skills. And by the way, if you're not sure how to do this, come to office hours. Right? This is something that's very important to get straightened out as quickly as possible. Right? So come to office hours. We'll be very happy to talk you through this. But make sure that you can write down the matrix that represents a quarter turn counterclockwise. And once you've done that, what you'll notice is that that's in fact what this function is doing. if you sort of forget about the whole vector field thing and just think of this as a vector in, vector out, it's literally a quarter turn counterclockwise. And once you make that realization, then now we know that it's this green vector right here. So for every point, you can think of this field vector as starting with the position vector and then rotating counterclockwise, and that gives you this. Okay. All right, so the result then is this vector field has this picture right here. This is what I like to think of as a stirred pot. You're looking straight down on a pot. Maybe you're going to make some pasta or whatever. And you've got the water stirred counterclockwise. This is about what it would look like. Okay. All right. Everybody good? All right, here's another one. Let's see here. There we go. So I'm going to start with that formula right there. This is the most compact way to write this one. There's a better way to think about the algebra on this, though, and that is to kind of break up that x magnitude of x cubed into an x squared and then a magnitude squared and then just a single factor of magnitude. When you do that, notice that what we end up with then is a unit vector and a scalar. And this is a really nice way to write vectors. If you can write a vector as a unit vector times a scalar, then the unit vector tells you the direction and the scalar tells you the magnitude. It's really nice. Well, assuming that magnitude is positive. So in this case, notice that the unit vector is always what we're going to call radial. It always points sort of on a ray coming out of the origin. Right? So this is a radial vector field. And then furthermore, the magnitude, you can see right here, is inverse square. In the sense that this scalar representing the magnitude varies with the inverse of the square of the distance from the origin. So that's inverse square. So that said, altogether, we call this vector field, given by this formula, a radial inverse square vector field. So now why do we bother giving a name to a highly specific example of a vector field? Well, it's because this particular one is extremely important. This is what gravitational fields look like, for example. Right? You think back to your high school physics or whatever, and gravity is inverse square, and it's always directly in the direction of the center of the Earth if you're talking about Earth's gravity, for example. Now, perhaps less known fact, this is also structurally exactly what electric fields look like. If you've never dealt with electric fields before, don't worry about it. It doesn't matter. It's fine. The idea is that a charged particle creates this thing called an electric field, and that makes other charged particles do things that physics people have to worry about, right? And engineers. So an electric field, same structure. So now I'm going to plant one last thought on this while we're on it. I think this is a really useful fact. When y'all are studying electric fields, I mean, let's face it, electric fields are kind of hard to relate to. Kind of hard to, it's an abstract construct. Charge is such a non-typical day-to-day, experiencing a charged particle, we just don't, right? It's not our day-to-day experience. It's so unrelatable that humans didn't even know about them until fairly recently, right? A couple hundred years ago. That's not that long. So they're really hard to relate to. They're really not viscerally sort of, relatable. But here's a trick that got me through a lot of physics classes, and that is, if you want to understand electric fields, just think gravitational fields. Structurally, they're the same. Different constants, sure. Different units, yeah. But structurally, electric fields and gravitational fields are just exactly alike. So again, big help for me when I was thinking about physics way back when. All right, what do you think? Everybody okay? Okay, gradients. This really is not that big of an observation. Old news, we know what this thing is called, a gradient. If you give me a function, then we can take the various partials, and this is the gradient. And the only observation I'm going to make here is that, in fact, this gradient, we hadn't thought of it this way at the time, but it's a vector field. At any given point, x comma y, there is an associated vector. So, vector field. How about that? Right? We didn't have any need to think of this as a vector field previously, but now that we're talking about vector fields, it's worth observing. So, in particular, if you were to look at the entire domain here, and notice that at every point there is an associated vector given by that formula, you'll notice that it's radially outward, right? Because it's basically 2 times that radial outward vector field that we saw earlier. So it points radially outward, maybe a little longer, twice as long, right? But still radially outward, about like this. And then you'll notice that this also tracks with another fact that we had discussed. Namely, if you look at the graph of that function, the gradient always points uphill on the graph. The gradient points in the direction of fastest increase. Right? So we previously thought of this 1 point at a time. Now I'm just going to make the observation that all of these gradient vectors, all as a vector field, are all simultaneously pointing uphill on the graph above wherever those gradient vectors are in the domain. So, again, nothing new, just kind of a new twist, new take on something we'd already seen. Yeah?
So, if you were to make a vector field out of that, it would still be in R2?
Yeah, that's right. So, that's right. Let me write this down. So, we have our original function here was from R2 to R1. And when we write the gradient, gradient is then a function from R2 to R2, right? Because it has 2 inputs and 2 outputs. Yeah. The inputs are x and y. The outputs are these 2 formulas right here. So R2 to R2, or said differently, it is a vector field on R2. So this xy plane down here is where the vector field lives. Yeah, totally. All right. Okay. Now let's talk terminology a little bit. This is, it's got to be done. Y'all aren't going to be shocked to hear this, but I have some non-standard preferences in terminology. Y'all have seen me do this before. So reminder, now when you take a gradient, there's the function that you're taking the gradient of, and then there's the vector field that you produce. Right? As we previously knew. Give me any function, there is a corresponding gradient vector field. So obviously what comes out is called the gradient. Of course it is. Okay, now let's ask, what should we call the function that went in? So instead of thinking, I have a function, what should I call what comes out? Let's turn it around backwards. Suppose I have some vector field. What is the function whose gradient produces that vector field? In other words, given something on the right, how do I get something correspondingly on the left? It's going backwards through the gradient operator. Now, I'm going to point out we've been in this situation before. In single variable calculus, derivatives. If you have a function, you take the derivative. The result is called the derivative. If you have a derivative and you want to kind of undo that, antiderivative, yeah. So, call me crazy. Seems to me that this input should be called the anti-gradient of the vector field F. Seems very natural to me. I am sad to report this is not the most common terminology. So the most common terminology, I'll get to momentarily, is based on the following fact of physics, and that is when you have potential energy and corresponding forces, then the gradient of the negative of potential energy is the corresponding force. And let's just think this through with gravity. If you know a little bit of mechanics, gravity pulls down. Right? Potential energy, therefore, is higher the higher up you go. So which direction does the gradient of potential energy point? Well, gradients always point in the direction that the function's increasing. So the gradient points up. But the gravitational force points down. That's just how the cookie crumbles. That's just how things are set up. Unavoidably, it's the negative of potential energy that is the anti-gradient. So in particular then, because the negative of potential energy is the anti-gradient, they refer sometimes to anti-gradients as potential functions. Now you can probably see already on the screen here why I don't really like this terminology. It's this minus sign right here. It's really confusing. If somebody says potential function, are they telling you the anti-gradient or are they telling you the potential energy function? It matters to the tune of a minus sign. There's a nasty opportunity for confusion there. So I think this is just a really unfortunate thing. I'll also point out, sometimes when we're talking about gradients, we are doing physics. Yeah, right, sometimes. Not always. Sometimes we're just doing math. Sometimes maybe we're doing some economics. There's no potential energy to be discussed when you're doing economics. I think it's very presumptuous to just go around assuming that we're always doing physics. We're not. Right? So I think this is highly suboptimal terminology. It's not wrong. I'm going to put a sad face on it though, because I really wish they wouldn't use that term. What I think is always reasonable, always makes sense, is the word anti-gradient. So just to let you know what you're going to be up against and what you're going to be facing in my class, you're going to hear me say anti-gradient most of the time. I will occasionally probably say potential function, just because that's something I heard so much, coming up. Very common terminology. Outside of my class, you're probably going to hear the word potential function, and I wish you the best of luck in keeping that minus sign straight. Right? So heads up. Watch out for that nasty little, easy little oops that you can make as a result of this unfortunate terminology. Okay. Alrighty. Moving along then. Here's a different way to think about vector fields. If you're going to define a mathematical object, it's nice to know what real-world thing are we talking about. And we've spent some time here talking about forces, right? So here's a couple of huge examples of how a vector field can be used to represent forces. And that is a wonderful way to think about vector fields. It's what I call a metaphor for vector fields. So here's another one, though, and that is fluid flows. In fact, I guess I did already kind of mention one of these, and that's my stirred pot here, right? Here I have a fluid, kind of, that's flowing around in a sort of counterclockwise flow. All right. So this is just another sort of physical example, and here's a bunch of them. If you're in space, if you're in 3 dimensions, as you know, that's where we live, of course, then airflow, the air moving around in this room, could be represented with a vector field, right? Because wherever you are in this room, let's talk about this point right here, this point right there, the air is moving ever so slightly. I wish it was moving more. We've got kind of a dead air problem in here, but there is a little bit of a velocity at this point. There's an associated vector, namely the velocity. That's what a vector field is. Likewise, in the ocean, at any given moment, any given location in the ocean, The water is moving with a certain velocity. So ocean currents can be represented with vector fields. And then various stuff moving around inside of fluids, like how does pollution move through the ocean, or how does it move through a lake or a stream or whatever. How does ozone move through the atmosphere? Stuff like that could be represented with a vector field. Okay. Now, we live in the three-dimensional world, of course, but we also live on a two-dimensional surface. Right? Surface of the Earth, approximately. Right? Maps are two-dimensional. Right? So things that are moving around on the surface of the Earth, pretty natural to think about as two-dimensional vector fields. So I like the one with animal migrations, and a lot of people will complain that, wait a minute, but a fluid, right? A fluid is, I don't know, it's not made out of things. It's made out. It's intrinsically like it doesn't have discrete pieces, right? It's a fluid. It seems contradictory. I'll point out any fluid that you've ever dealt with before actually is made up out of little bitty pieces. They're just really, really, really small. They're molecules, right? Water is made up of molecules. It's little particles. So, sure, if I'm talking about a migration of, some kind of birds that are flying around as a flock of, 5 million birds or whatever it is, or a swarm of locusts, right? Sure, they're technically bigger particles, but it's still kind of a fluid, and they do still kind of flow along together. It's actually very fluid-like. Okay. All right. So here is a related idea. There's a calculation we're going to go through here in just a minute. Get to the calculation in a moment. Let's first set up the context. The big idea here is that if you have a vector field representing a fluid, and specifically the vector field represents the fluid by indicating velocity. Not that that's the only way to do it, but let's just say for the purposes of this example, we have a vector field that represents the velocity of a fluid. A reasonable question that I could ask is, given some area, some little flat surface like this, and given that the fluid is flowing, like so, let's assume, by the way, that our area is not a solid, don't think tabletop, right? Think like a screen, something that's permeable, something that air can pass through. Right? If I have a screen representing a surface, and if I have a flow, I can talk about, well, how much air is actually passing through that screen. And the way we would measure how much air is passing through that screen would be in terms of volume of fluid per unit time. Right? So it's going to depend on the area in particular. All right, now here, just as an example, let's talk about the fishing nets in the ocean, right? And so they're out in the middle of the ocean. They got some net hanging down there, right? Well, to whatever extent the current is passing through the net, that's going to cause volume of water to pass through the net per unit time, and the more volume of water is passing through the net, the more fish you're going to catch. Right? Does that make sense? Whereas if the water is not going through the net, if the water is going parallel to the net, you're not going to catch any fish that way. That would be a silly way to do fishing. Does that make sense? Okay. So this is a pretty physically natural thing to want to talk about. Very importantly then, we want to distinguish between these two somewhat related objects. The distance per unit time indicating the velocity of the fluid, and then the volume per unit time representing the what we call the flow rate of the fluid. Okay. Another example, and I just looked this up because I find this entertaining. You can think about a river, right? I like to I think it's interesting to look at the Amazon River, right? Very important in the ecology of the world. And how fast is that water moving? It's not like a rapids kind of a situation, right? It's just doesn't really move that fast. But there's an unbelievable amount of flow rate, and I've already forgotten the numbers. I think I remember seeing that it was over 200,000 cubic meters of water per second flows through the Amazon. So that's a tremendous amount of flow rate because of the size, right? Even though the velocity is not particularly great. How are we doing? Everybody? Yeah.
Just one small question.
Yeah.
I'm a bit confused at how you went from that.
I'm going to go through all of this in just a second. Yeah. Okay, but I just wanted to talk first about what is it that we're trying to compute, and now we're going to dive into the details here. If you want to compute volume per unit time, dividing by time is going to be the easy part. That delta T we're going to end up with, we'll just divide that off. So how do I get the amount of volume here? Well, this volume is, I'm going to say pretty believably, height times area, right? Height times area. Actually, let me zoom so we can see better. Height times area. Is it just me, or is there a... Okay, all right. Wanted to make sure I wasn't losing my mind. Okay, so height times area. What can we say about this height? Well, the height is going to be in the direction of what we're going to call the unit normal vector. Unit normal vector is a tool that we use to describe how an area is sitting in space. This is what we call an orientation. So if you'll notice the way my hand is sitting in space right now, just knowing that vector, represented by my stylus here, tells you how my hand is arranged in space. And if you know that that vector is like that, then you know that my hand is oriented like this. Right? So this vector that you use to represent the direction perpendicular to your surface, called an orientation. And it's typically used, we use a unit normal vector. Okay, all right, now that said, what can we say about that height there? And I claim that I'm going to use blue here, that it relates to this displacement vector. And this displacement vector says, you've got to keep in mind, we're talking about a fluid that's moving with this velocity, right? For an amount of time, delta t. This d represents the total displacement then that moving with that velocity for that amount of time gives you, and that I have gotten ahead of myself. I'm sorry, I went out of order here just a little bit, but let me just write this down. This displacement vector is F times delta t. So let's set that aside for just a moment. Again, I accidentally got ahead of myself. Sorry. All right. So what can I say about the height? I claim that the height is the normal component of that displacement. Everybody see that? Let me just again for color coding. There's the displacement, and we want to look at the component of the displacement in that perpendicular direction. That gives me that. Cool. Components, of course, are computed with wrong color. Components are computed with dot products, and dot product, in particular the D part of this dot product, is as we just discussed right there. What do you think?
So the F in this equation is the function F of X, right?
It's the vector field representing the velocity of the fluid.
Okay.
Yeah. Right. Okay, so altogether, everything else just kind of follows along, and so our final result then for this flow rate, let me clean up this big mess. Given a velocity, the flow rate, volume per unit time, is given by this expression right there. And so this is actually a really important calculation. It turns out there's a lot of situations where you have a fluid of sorts, the sort depends on the physical situation, and you need to know the volume per unit time or quantity per unit time of the fluid flowing through a given surface. And this formula is going to be very, very critical in being able to analyze those situations. So when things are this important, they deserve a name. In this case, the word is flux, and we use the capital Greek letter phi to represent it. And do make it capital, please, to distinguish it from the spherical quark. Okay. Everybody all right? Okay. Now, here's what I'm going to leave as an exercise for y'all. I think this is a really healthy exercise. As always, don't forget, if you get stuck on this, come to office hours. Very happy to help you think this through. We're going to change the question. This had us representing the fluid by way of its velocity, and then flux gave us volume per unit time. We're going to ask now an analogous question. What would you get if instead of representing the flow by velocity, what if you represented the flow by density times velocity? And what I want y'all to do is to go through something kind of like this. In fact, it's going to be extremely similar to this. It's going to, in fact, be exactly this, where density gets inserted appropriately. You got to think about how, where and how that goes. What you're going to find then is that in this situation, flux, instead of giving you volume per unit time, now will give you mass per unit time. So nice little exercise. The calculation is very, very similar to exactly what we have here. Just insert density. Think about where you need to insert density. Insert it. It will eventually be reabsorbed into the vector field, and you will get exactly this result. Great details to think through. Give it a try. Okay. All right. Let's see. By the way, I have no idea how we're doing on time here. Never as much time as I think. Okay, so real quick, we're not going to do this whole page. We don't have time. This page is pretty optional, but I just want to address a scenario that is actually pretty important. That's not really something that's part of this course, but it's going to come up in your engineering and physics courses pretty significantly. So here's the idea. Suppose you have light bulbs. For example, here's a light bulb, and of course that spits out a flow of photons that, again, you could think of as being kind of like a fluid, isn't it? It's a different kind of a fluid. It's not something you can feel, right? But nevertheless, it's a bunch of little teeny tiny particles that all kind of tend to move roughly together, as is a flow of water, as is a flow of air. So photons created by a light bulb are a fluid. Okay, now what if you have a second light bulb, right? And that one's spitting out photons too. Now I have kind of two fluids kind of mixing together, and the question is, how would I represent this total fluid at that point? Can I talk about the velocity? Rhetorical question. Can I talk about the velocity of the fluid at this point? And I point out that no, I really can't. Because at that point, there's going to be some blue photons going that way, and there's going to be some orange photons going that way. So at this point, photons are going different directions at the same time. Water cannot do this. That's not how water works. Right? At a sufficiently small scale, all the molecules of water are kind of moving together. Likewise, air cannot do this, but photons can. Photons can pass right through each other. So I can't talk about the velocity here. The neat trick that I want to point out is that you can still use a vector field to represent this kind of a fluid flow. And the trick is to remind ourselves that we have this formula down here. right? And we've thought about this formula so far as if you give me a vector field, then I can compute the flow rate. You give me a vector field representing velocity per unit time or density times velocity or whatever, and I can compute volume per unit time of fluid flowing through an area. What we're going to do here is just turn that around backwards and say, look, for whatever area we're talking about, I can empirically measure this flow rate. That's just a matter of a little time in the lab, right? You can just see exactly what that flow rate is. And given what those flow rates are, you can reverse engineer and find that there will always be exactly one unique vector field that will make this equation work. And so even if the vector field doesn't represent the velocity or density times velocity at all, you can still use a vector field to represent wacky fluids like this one here. So super quick, I'm going to basically, if I can get this thing to cooperate, there we go. I just want to point out that this example down here is a lovely, clever example that's really interesting and very relevant to some stuff that you'll see in physics classes here and there, and really cool calculation, very nice tricks, and we don't have time to do this. So among the tough choices that I have to make, I am excusing y'all completely from this example. It's not that I'm not going to talk about it in class. It's that I am not going to talk about it in class, and you're not responsible for it in any way. So feel free to skip this. That said, if you're curious, come talk to me. It's very cool. I'd love to talk to you about it. Y'all have a good rest of your Monday. See you later.